having worked out how to actually set a pin high or low, let's look at actually driving some loads with our microcontroller, actually driving some real hardware. There's lots of different things that we can drive with our microcontroller, but one thing that we need to keep in mind is they're fairly low current devices. They can sync signals or take in current, or they can source signals, they can output current, but not very much. So for our particular microcontroller here, we can only source or supply about 12 milliamps across a particular port, so all 8 pins in the port. And we can sync about 48 milliamps across a port. Not very much indeed. So we can connect a whole bunch of indicator LEDs, some low power, low current LEDs, and sync them fairly easily. So we'll put a few on a particular port. But anything higher, if we want to drive a motor or something like that, it's probably going to be too much current for us. And so we need to come up with some sort of other arrangement, whether it be a relay or transistors or field effect transistors, something like that. And we'll talk about those later on. But firstly, LEDs. And driving LEDs is something that we do all the time, very common, and it's probably the most basic indicator that we can have with our microcontroller. Now, LEDs vary quite a bit. They vary in the amount of current they can do, vary in their color and their intensity. They can also vary in the forward voltage or the voltage required to turn them on and display a light. Typically, this voltage varies from about 1.7 right through to about 4 volts, and it's often dependent on what color that we're actually dealing with here. And once we hit the forward voltage, once we hit the voltage where current starts increasing a bit and we have some light from it, a small increase in voltage beyond that, as we see in the graph, results in a very large increase in current. So we actually want to limit that current to typically the between 10 to 30 milliamps or so that we want for our LEDs to produce enough light so that we can see them. Now, we've already said that digital logic, and we've seen this in our previous slide, can sync more current than what it can source. So typically this is the way we connect up our LEDs to our microcontroller. And we've got a circuit here. We can do some simple node voltage analysis around this circuit to work out the value of our current limiting resistor, our resistor R there. So we've got VCC, which is our supply voltage, whatever we're using. We've got our current limiting resistor R there. We've got our LED, there's a symbol for an LED there, and that's being synced into our microcontroller. So if we know the forward voltage of the LED, we can read that from a data sheet, and we know our desired current that's going to be flowing through that LED, we should be able to easily work out a value for R. Now remember, we do node voltage analysis. We've got one current path here. The current's going to be the same flowing through the LED as the resistor. So essentially we need to work out what voltage drop we need across the resistor to give us the required current limiting ability. So let's work it out. If we draw in some variables here, if we say IF is the current, the forward current flowing through both the LED and the resistor, we have VF, the forward voltage across the LED. We have VA, which is a node there between the LED and the resistor. We can work out what our resistance is going to be. So it's VCC minus what we call V output low max, which is the maximum voltage the microcontroller will put out when it's putting out a low signal. Now typically we assume this is 0. It's actually not 0. It's close to 0, and we want it to be close to 0, but it might be 0.1 volts or 0.2 volts or 0.3 volts, some very low value, but it might be a little bit above 0. So we call that V output low max. In the questions, if we don't specify V output low max, or in the exam, just assume it's 0, and that's a reasonable assumption in many cases. So we've got V output low max there. So VCC minus V output low max minus VF, so the voltage across the LED, divided by IF. Now think about it for a moment. Essentially what you're doing is you've got your supply voltage minus the voltage across the LED minus the voltage that's above our ground voltage. We've subtracted all the voltages. The only voltage left there is the voltage across the resistor. So we've just got a basic form of Ohm's law here. R equals V, voltage across the resistor, divided by I, voltage, the current through the resistor. We're left with what our resistance will be, or what our resistance needs to be to perform that current limiting. Let's go through a basic example of it. So we'll say, in this case, VCC is 5 volts, V output low max is 0.2 volts. Our forward voltage is 1.7 volts, and our current that we're aiming for here is 15 milliamps. If we put it all into the equation, we get 206 ohms. Now, we're not typically looking at 206 ohm resistors, so we either go a bit above or a bit below, so maybe 180 ohms or 220 ohms. They're both acceptable values that will give us a suitable amount of light and something in the order of 15 milliamps current limiting through here.
Now, one thing we should mention is the LEDs are connected again in a syncing arrangement. So we have the current is synced into the microcontroller rather than sourced out. And this makes turning on and off the LEDs slightly counterintuitive. If we output a low down here, so we output a 0, we'll be turning the LED on, because think about what we've got here. We've got a high voltage here, 5 volts or 3.3 volts or something like that. We've got a low voltage here. We can actually have current that flows through here into our microcontroller. Our LED turns on. Conversely, if we output a high here, or a 1 or 5 volts or 3.3 volts, whatever we have, and we've got the same voltage up here, do we have any current flowing from here to here? No, we don't, because it's the same voltage here and here, and our LED will turn off. We need a voltage drop to occur from here to here. So, if we want to turn our LEDs on, we set the output of that pin to 0. If we want to turn them off, we set it to 1.
But what if we want to have a whole lot more current flowing through here? Maybe we want hundreds of milliamps, or maybe we want amps. Well, then we need to go with something a bit more substantial. One way we can do it is with a relay. Now, a relay is essentially a little electromagnetic switches. You may have remembered experiments from high school science where you had an iron nail, you wrap a piece of wire around it, you put a battery on it, and it becomes an electromagnet. It's a magnet where you're connecting the battery and you can pick up paper clips and things. But if you're not connecting the battery anymore, it stops being a magnet anymore. Essentially, these relays have a little electromagnet inside, and if you supply current to them, it becomes a magnet and pulls a contact over and closes a switch. If you don't supply current to it, a spring will push the contact back in the other direction and open the switch, and you can switch large amounts of current, even tens of amps, with something like a relay. What we normally do, though, is we need to drive them with some sort of a transistor. Normally we need dozens or hundreds of milliamps to actually turn on one of these relays and energize this electromagnetic coil. So we can't just connect it to a microcontroller pin generally. We've got a few other components around here. So we've got a transistor here where we're driving it like a switch to turn on and off our electromagnet. We've got a little diode there. It's called a flyback diode that prevents when the electromagnetic force collapses when we de-energize the coil. It stops all that current flowing back in and destroying
the transistor.
We have R1, the resistor 1 there, it's a current limiting resistor, and we have a resistor 2 there, which is a pull-down resistor, which means that if our microcontroller is on startup, for example, it's not driving that particular pin, it will pull it low and not turn the transistor on, and hence we won't actually energize our relay and turn something on at startup, for example. Now, relays have a few problems with them. They're pretty slow. They're slow to switch on and off, and they're actually pretty noisy. Both acoustically, you actually hear them switching on and off. You hear a click, 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 click as they turn on and off. But also electrically noisy. They generate a fair bit of electrical noise as they switch on and off like this. And hence, they're a mechanical device. They will eventually wear out. These contacts will get dirty over time. They're switching on and off. They'll wear out over time and need replacement. Now, that might be 1,000,000 cycles or 100,000 cycles, so it may be a very long time. But we have other ways around this, other semiconductor ways around this that are a lot quieter, waste a whole lot less current, and actually work fairly well for us. Now, one of the ways is what we call field effect transistors. Now, field effect transistors are essentially types of transistors that have very, very low on resistance. So a typical BJT transistor that we looked at previously might have an on resistance of an ohm or up to 5 ohms maybe. Now, if we're switching really small currents, it probably doesn't matter very much. But if we're switching a few amps and we've got an ohm or up to 5 ohms of resistance there, we're going to have a large voltage drop across that transistor, which will just heat up and will actually just be a waste. Typically, our field effect transistors are in the order of milliohms, so tiny amounts of resistance there, and tiny voltage drops we'll have there. We won't be wasting a whole lot of current across these transistors. So here's an example of a field effect transistor. This one's what we call low side drive, where we have a field effect transistor Q2 there. It's got a load below it, so it's switching power to that load and switching power from that load. And here we've got a microcontroller connected to a transistor that will drive this field effect transistor. And some of our field effect transistors can be directly driven from a microcontroller, and we don't need this essentially inverting configuration of a transistor there with a pull up there to the high voltage. Now, something else that's useful for us at times is we want to drive things in two different directions. For example, a motor. And one configuration that we can use to do this, the one that we normally choose, is a H-bridge, where we have 4 transistors or relays or field effect transistors, and if we turn 2 of them on, 2 opposing ones, we can make the current flow in one direction through, and if we turn the other 2 on, we can make the current flow in the other direction. So we can make a motor turn in one direction and then make the motor turn in the reverse direction. Those options are available to us. There's a little submarine there that I built a number of years ago, and the main thrusters in this used some H-bridges to actually drive those thrusters and actually control the thrust in forward or reverse direction. Typically we'll have these in a little package. We won't have individual field effect transistors that we use.